Hello everyone, myself Uma Sharma from IIT BHU under the supervision of Professor Prabhakar Singh, going to present my contributed paper on the topic of electrical properties of LASRTIO3 as SOFC electrode material in the International Conference on Energy Material and Devices ICEMD-2022 organized by the Mahila Mahavidyalaya BHU. These are the overview which I am going to discuss. First of all, I would like to give a small introduction about what is fuel cell and why we need it. As we all know that, we are at the edge of the conventional energy sources, and the energy demand in the energy market of the due to the economic growth is increasing day by the developing countries in all over the world. So, fuel cell is an alternate energy source to it, since it has no any waste and the harmful byproduct. So, it is a clean and green energy. So in general, we can say that fuel cell is an electro device which converts the chemical energy into the electrical energy without any harmful byproducts. There are number of fuel cells depending upon which type of electrolyte we are using. So here we are working on the solid oxide fuel cell, and it is a complete solid state device which uses an iron conducting ceramic as its electrolyte, and it operated at high temperature from 500 to 1000 degrees Celsius and gives a high efficiency and relatively low cost in the comparison of other fuel cells. This is the systematic diagram of solid oxide fuel cells. Its microstructure and the conductivity relation. Here, the working of fuel cell in general is that hydrogen atoms enter at the anode, and the chemical reaction splits into their electrons, and the ionized hydrogen atom have the positively electrical charge, and the negatively charged electrons provide current to do work. So here, these are the basic of the of any fuel cell, that are the electrode and the electrolyte, which have some electrical and thermal mechanical properties. In electrodes, the electrical properties in the electrode, we need a high conductivity, which may be mixed ionic and electronic, and in thermochemical, it has porous in nature, because it is the basic requirement of an anode or especially electrode to any fuel cells to provide sufficient active sites for the oxidation of the fuel. So these are the requirement for a materials, like for the these are the requirement for a material for the electrode and the electrolyte. Therefore, electrode, the electronic conductivity and the ionic conductivity both are required, but for electrolyte we need a high ionic conductivity in comparison to the electronic conductivity. So the question is that why don't we go outside and buy a fuel cell? Problem is solved. No, problem is not solved, because there are different designs, and there are different designs and shapes, and the technical issues vary kind to kind fuel cells, and also we are constrained to the choice of the fuel cell choices. We are constrained to the choice of the which type of electrode and electrolyte we are using. So what motivated me to because for the very long time we are using this type of electrode and electrolytes for the fuel cell, and we all are familiar to the nickel cermet made of yttria stabilized zirconia based anodes, because they have the high conductivity and very porous in nature, and also stable and thermal expansion compatibility of thermal expansion coefficient. But they have some drawbacks such as carbon deposition and contamination issues, and same as LSGM and IO, which is an old composite material but is less compatible. So what we need for a better electrode performance is electrocatalytic activity for oxidations, thermal and chemical stability, also high ionic and electronic conductivity, compatible thermal expansion coefficient, and so lanthanum, cesium, and these type of material possess the highest conductivity in AbO3, and also by increasing the charge we can enhance its conductivity, like substituting the lanthanum in the strontium, it increases its conductivity. So here in this present work, what we have done, we have chosen this strontium titanate, and will substitute lanthanum in this, and it will include and will study some electrical properties of its. Strontium titanate itself, it's a promising material for widespread applications like electronics, energy storage devices, and also via substitution of any donor impurity we can increase its electrical conductivity. So what is the methodology? We have synthesized here the materials via solid state reaction route, and we have calcined at 1200 degrees Celsius for 2 hours and also sintered at 1300 degrees Celsius for 2 hours. And this method is better in compared to the other process. For the characterization, we have the structural characterizations like phase formations and XRD, morphological and microstructural characterization like SEM and CAM. And also here we have performed electrical studies via LCR meter, and calculated all the electrical properties of material at different frequencies and the temperature. So what we have analyzed here, this is the we have analyzed the frequency dependent conductivity spectra of LST at various temperatures, and here the symbols represents the symbols represents the data points and the solid lines, and this solid lines shows the data fitted points via Johnson power law. So figure clearly shows that K for the first plateau corresponding to the bulk conductivity and caused by the random motion of the mobile charge carriers, and the dispersal regime shows the AC conductivity caused by the correlated forward back hopping motion of charge carriers. So here the reciprocal of the temperature with the bulk conductivity and the hopping frequencies was the RNS representation, and these activation energy values are found by the least square fit data of data points. And here the EH values of 1.77 electron volt and 1.39 electron of hopping hopping shows that the concentration of mobile charge carriers is independent of temperature, as well as conductivity is determined primarily by the mobility of the charge carriers, but via the activation energy of the bulk conductivity is 2.15 electron and 1.37 electron volt. And it shows that here the conduction is due to the oxide ion through the oxygen vacancies. It means that the oxide ions are mainly involved in the conduction as the charge carriers. Here the variation of the value of concentration on the mobile charge and the temperature here, and also the exponent graph has also drawn via the fitted data points of the JP law. And here what we've seen in this graph, that with the temperature the concentration of the mobile charge and increases. It represents that there is some charge carriers those are thermally generated, if then it shows some mixed ionic and electronic behavior. Also the DC conductivity versus hopping frequency, here you can see the slope is 1.13, which is nearly almost to the unity, and it shows that the DC conductivity and the hopping frequencies are approximately proportional to each other, and it means that conductivity is governed through the hopping as well as through the some other method like temperature. So here again, when we study the IV curve at room temperature for the leakage current, it shows that doped SRTO3 or lanthanum substituted SRTO3 shows the higher leakage current in comparison to the SRTIO3. So what we concluded that for the conductivity observed in LST is increased with activation energy range in the design, implying the band conduction, and also IV curve shows that it has the higher leakage current, and with the in unsubstituted value of SRTO3, which shows that it may be a promising candidate for the LST, promising candidate for the electrode and electrode, especially as anode. Thank you. These are the references.